Look at that. This time you get to look at my awesome face. Is there any way to move this thing? Whatever. I hate it. I don't like the webcam thing. All right. Back to business. This is 62 through 65 on the August 2015 Chemistry Regents. Looks like we're getting to some nuclear chemistry. So nuclear radiation, I'll pick green. Cool. All right. So one fission reaction for uranium isotope 235 is represented by the balanced nuclear equation below. So let's look. You have uranium with a mass of 235 and 92 protons get struck by a neutron, high energy neutron. And if you notice, the uranium atom basically broke down into a xenon isotope. So xenon isotope 140, strontium isotope 94. And if you look, the reaction also spits out or emits two high energy neutrons. Continuing reading, it says both radioisotopes produced by this fission reaction also undergo beta decay. So basically, you start with this radioactive isotope. That nucleus got hit with a high-energy neutron and broke apart into these two. They're called daughter particles. This is called the parent particle right here. And the large uranium nucleus broke into two smaller nuclei and also gave off two more neutrons, which these two daughter particles, xenon and strontium, it says they both undergo beta decay. So those are still radioactive isotopes. Okay, the half-life of xenon 140 is 13.6 seconds, and the half-life of strontium isotope 94 is 1.25 minutes. All right, first question, 62. Explain in terms of both the reactants and the products. So recap on that. The left side are the reactants, the right side are the products. So in terms of both reactants and products, why the reaction represented by the nuclear equation is a fission reaction. Well, the word fission and even the word fissure mean for things to separate or to crack. So we can explain that we see a large nucleus with a lot of mass broke down into products that have less mass and less protons and neutrons in each one. That's really it. So to save you some of my awful handwriting, I will type that up for number 62. So this is number 62. And again, explain in terms of reactants and products why the reaction represented is a fission reaction. So this is nuclear fission, releases a lot of energy. Okay. The reactant, which is uranium 235, is that what they used? Yep. So the reactant uranium 235 nucleus broke down, or you could use the word decomposed, into two smaller nuclei. Is there another way we could state that? The products have less mass, meaning they have less protons and neutrons than the original reactant nucleus. Again, anything along those lines, as long as you're explaining yourself scientifically and you are mentioning both the starting atom and the atoms you end up with, the nucleides, you should be marked correct. So any way that you can explain that you saw a heavier nucleus breaking apart into smaller nuclei, that is correct. The only thing that would cause you to lose points here is if you only mention the reactant or if you only mention the products. You have to mention both. So the heavy uranium nucleus broke into smaller xenon and strontium nuclei. That's fine, right? The larger uranium 235 nucleus broke into smaller xenon and strontium nuclides. Here you go. Next, complete the equation in your answer booklet. Okay, I'll have to go to the answer booklet. For the radioactive decay of xenon 140 by writing a notation for the missing product. Before I even look at the equation, I'm going to go back to the reading, and it says right here that xenon and strontium both undergo beta decay, so they both give off high energy electrons out of the nucleus. Okay, so I'm actually going to have to delete all this, exit, and go to the answer booklet for you. Okay, so let's go back to, okay. Or actually, better yet, I will go to the answer booklet right here. Hang tight. August 2015. Answer booklet. Okay, and now this is question 62, 63. Okay. There we go. So there is the beta particle that they were mentioning. See, this is a beta particle, which is a high-speed electron. Okay, so quick recap. Energy and electric charge and mass cannot just appear out of nowhere, and they cannot just disappear into nowhere, as far as we can tell. Meaning, an equation has to be balanced on the reactant side and on the product side. So basically, we have to figure out what the missing mass and the missing charge are. When you have particles on opposite sides of the yield sign, that's the yield sign, you subtract to find the difference between the two sides. So let's do it. Let's subtract the mass first. So 140 minus 0, the missing mass is 140. 54 minus -1, be careful, 54 minus -1 is really 54 plus 1, which is 55. And now, one last step, we have to figure out what element 55 is. And I spy radioactive cesium 140. So cesium. Yeah, so when you're finding the missing particle, you can't just randomly throw whatever symbol. You have to find the element with the correct number, the atomic number, the number of protons. So that would be cesium, and the mass is 140, and the proton, the charge in the nucleus is 55. Okay, cool. All right, now I'm going to delete all that. Go back to the questions. Let's go back to the exam. No, we went back to the answer booklet, not what I wanted. Back to the exam. Okay, now for number 64. Determine the amount of time, what happened? The amount of time required for an original, so we have 24 grams of strontium-94. How much time would it take for this much of strontium-94 to break down, to decay, until there's only 1.5 grams left? Okay, there's a hard way and an easy way, or a longer and a shorter way. I'm going to do, let's do it the long way. So one longer way to do this is to set up a table with 3 rows. So I like to set it up as how many half-lives, how much time has passed, and the amount of stuff that is still radioactive. So half-lives is always 0, and pretend like no time has passed. 0. So no time has passed, no half-lives have passed, and you're starting with the original amount of 24.0 grams that are fully radioactive. Okay. And actually, I'm going to scroll a little bit here. If we go back to the reading, we are given the info here that the half-life of strontium-94 is 1.25 minutes. Okay, so we're going to have to use that. So Going back. So 1/2, oops. Sorry, clicked on the wrong item here. 1 half-life is 1.25 minutes. And the reason why it's called half-life is because the amount of atoms that are still radioactive after 1 half-life is half the original amount. So a half of 24 is 12. We have to get all the way down into 1.5 grams. So a faster way to do this is to go, okay, 2 half-lives. I know that's going to take me another 1.25 minutes. So 1.25 plus 1.25 is 2.5 minutes. And that's half of 12 is going to be 6 grams are still radioactive. And again, if I keep doing it the long way, 3 half-lives is another 1.25 minutes. So that's 3.75 minutes. And half of 6 grams is 3 grams are still radioactive. Again, not done because the question says how much time passed until only 1.5 grams are still radioactive. So 4 half-lives, that's going to be plus another 1.25. So that's going to be 5.0 minutes. And half of 3 is 1.5 grams. So there we go. The amount of time that it took for the sample to decay to only 1.5 grams that are still unchanged or still radioactive is 5 minutes. Yay. That's it. And let's try to tackle that last one and wrap this up. So question number 65. And again, I'll have to go back to the answer booklet. It says, on the diagram in your answer booklet, draw an arrow to represent the path of an emitted beta particle in the electric field between two oppositely charged metal plates. Okay, let's find question number 65 on the answer booklet. So, answer booklet. Hello. Oh, answer booklet. There we go. Sorry. Answer booklet. Come on. All right. Oh, yeah, and then the answer for number 64 was 5 minutes. All right, now here. So a beta particle. Okay, I mean, I'm pretty sure we know this by now, but just to double check something, if you don't remember, go to table O and find a beta particle. Just try to remember, a beta particle is really just an electron. So there we go. Beta particle is negatively charged. So we know that opposites attract. So if we have a negatively charged, right, electron, beta particle, it's not going to move towards the negative plate. It's going to be repelled, and it's going to be attracted towards the positive plate, which means that the beta particles are going to go like that. They're going to be repelled from the negative side and attracted towards the positive side. So any sort of drawing that shows that the beta particles are negative and will be attracted towards the positive plate and repelled from the negative plate. That's it. As a matter of fact, this experiment is how we figured out that there are different types of radiation with different electrical charges, is by passing the radiation through two plates with electric fields. And the first type found was alpha particles, which are positive. The second type found are these, which is fast electrons, beta particles, and they're negative. This is how we found out. But that's it. That's the answer.